will record this, again, this part. So now what I'd like to do is to see how each of those network types affects that histogram. So to do that, we could go down here for network type, and we chose random. Now I'd like to choose a ring lattice network. We'll leave it the same 5 connections per agent, and we'll run that. How did I get there? I went to main. I scrolled down in main and set network type to be ring lattice and set it to be 5 connections per agent. Okay? And we're going to run this again. So now we're going to have a ring lattice, a lattice where people are connected to others next to them. And here, each person has exactly 5 connections to others. It's very localized, one-dimensional form of locality. You're connected with neighbors to the left and right. I'd like to choose a network type small world, which is going to have a certain number of, it's like a mixture of a random network where any 2 people are connected with a certain probability with a very localized network. So a random network has global connection. 2 people are connected regardless of where their spatial locations. By contrast, in a ring lattice network, people are only connected with people next to them. A small world network is like a mixture of the 2. We have a certain number of connections per agent. Those are mostly local, but in 95% of the time, but 5% of the connections are rewired. So let's look at what that looks like. Here is a small world network, ladies and gentlemen. Most of the connections are to people nearby, but some of the connections are long distance. Do you see that? Okay, ladies and gentlemen. Good. And finally, we will check out another type of network that is built into any logic, which is a scale-free network. And we'll leave the M to be 10 here, and we'll run this. And a scale-free network is going to have the property of having most connections are going to have, most individuals will have fewer connections, but some individuals will have lots of connections. I should have shown this before in terms of the graph for small worlds, but here we have this characteristic long-tailed distribution in the numbers of connections. Most individuals have smaller number of connections, some individuals have lots and lots of connections. So this is power law distributed, meaning the probability of having k connections varies as k to the minus gamma. Meaning, and no matter how many connections you have, if you consider the probability of having k connections versus 2k, the ratio of those 2 probabilities will always be the same. So maybe if you have 1 connection, you're only half as likely to have 2. Then if you have 100 connections, you're only half as likely to have 200. So it's a long-tailed distribution. It exhibits power law scaling. It's scale invariant. There's different terms used for scale-free networks. Yes?
Is it assumed then with the random that it's a normal distribution?
No. With a random network, it's a great question. With a random network, let's go back and impose a random network. We can go look at it. The distribution is something that's emergent from the generative properties, and it may look normal, or actually in this case it doesn't look that normal, but with a random network, the general rule is that any 2 people in the entire space have a certain probability of being connected. It's regardless of where they are physically in space, they have a certain probability of being connected. And as a result, you're going to have something like actually for each person, the number of connections that they're going to have will follow a binomial distribution, because each other person in the population, they're going to have this probability P of being connected to, right? This person, this person. So if we consider a population of size 1,000, each person is going to have 99 flips of a coin, of a weighted coin, as to whether they're connected with that person, that person, that person, that person. So each person is actually going to have a binomially distributed number of connections. And here we're going to have a variability then that's not normal in character. It's binomially distributed because each of those other people will be connected to me with a certain probability. And therefore it's not a normal but a binomial distribution. Is that helpful? Okay. Any other questions about that? So we have these different types of networks. And I want to highlight one feature though. So for one type of network, to a distance-based network, who you're connected to depends on where the other people are located in space. By contrast, there's a type of layout, a spring mass layout, where you're located depends on who you're connected to. So these are not two totally independent things, the network type and the layout type. But a ring network lets you see the structure of this network more easily. Okay, so ladies and gentlemen, I'd like to complete this little example. We've seen an extra output mechanism. I'd like you to go to person, and I'd like to build an infectious state chart. I'd like to go through that example we did yesterday, just quickly and remembering what we did. So suppose I want today to have a SIR state chart. Susceptible, infected, and recovered. Okay? Not the SEIR one that we had yesterday. How would I do this? So where do I go to add that states? The states in the state chart. Let's just rehearse these basics. So where would I go?
Palette agent state chart.
Good. Palette agent state chart, or you could do this state chart palette on its own. Okay, so let's add this in. We need an entry point. This is going to be called infection state chart. And we are going to add in a state here, which is going to be called susceptible. And we're going to add in a state which is called infective. And we're going to add in a state, ladies and gentlemen, which is called recovered. Okay? Great. Now, let's just go through, again, rehearsing what we did yesterday to build up that memory. Okay, so suppose we have this. We want to now have transitions between these things, okay? So there's going to be a recovery transition from infective to recovered, which is going to be dependent, let's say, on a timeout. And we suppose we want this timeout. Well, okay, we'll set it for now to be 3 days. Okay, 3 days. Great. And now we want a connection from susceptible to infective, which is going to represent infection. We want to show the name here. And this will be based on a message transition. And for now, it will be unconditional. Okay? Okay? So here we go. And we have a timeout. Okay. So what are we still missing here in terms of basic mechanisms? So if a person is susceptible and they get a message, they will go to infective. What are we still missing in terms of having the infection spread? Does anyone remember from yesterday?
Transmission.
Transmission. So how are we going to add transmission in? Who remembers from yesterday?
Just adding the extra transition.
Yeah, an internal transition. So that's right. Good. Okay, there we go. Excellent. So we have a transition here. So who needs Krugerian help? We're going pretty fast here because we're just covering over past material here. Okay, so we want to transition an internal transition that's going to be called contact Okay? And that transition will go off at a certain rate of, say, 1 per day. Okay? 1 per day. Great. Okay? And what needs to happen at that transition? What needs to happen to actually make something happen when it transitions, to make it a contact? What do we need to do? Does anyone remember from yesterday?
Send a message.
Send a message. We need to send a message. So let's send that message, okay? So we're going to have send to random connected, and the message will be, really use an option list for this. I showed you that yesterday, but I want to do this quickly. So it will be, in this case, it will be called exposed. Now, with the exposed message, if the person who receives it is susceptible, what will happen this time? If a person who gets this message is susceptible, the person who's sending is in this state. The person who receives it may be in this state. What will happen when they get that message? Anyone?
Will become infected?
They'll become infected. For sure. Because there's no... Remember yesterday we had a branch? To have because it was uncertain whether they get infected. Right now they'll get infected. So we can imagine it's some infecting level of contact. Okay? Okay. Ladies and gentlemen, we're just about done with the basics of this. This is good. But I would like to ask, what is still missing from this? We need to start what? One infective. One infective. And let's do this a little bit differently than yesterday. Okay? Let's do it a little bit differently than yesterday. Let's suppose we want to start a certain fraction infective. How are we going to do that? It's a common need, right? You start a population. How are we going to start them infective? They don't always start in one state. Well, it turns out this is yet another use for that important construct we saw yesterday, which is the branch. Okay? Okay. Ladies and gentlemen, we're going to have one branch that goes to susceptible and another branch that goes to infective. And this is going to be based on some initial state. Okay? Some initial state. Okay. So this branch here will be called, this will be the condition branch. This will be called initially infective transition. And this one will be the default. Okay? So we're going to have now, this is a way of dividing up the initial population, so some of them are infective and some of them are not initially infective. Okay? Great. Terrific. Okay. So we're getting almost all the way done here. I mean, we're getting very close to having this complete. But we need a couple more things. First of all, we need some way of sort of determining whether they go this direction, okay? So I'd like to go to palette, and I'll show you one way to do that. One way is to put in a parameter, is initially infected. Now, because I saw is, it's going to be true or false. How do we denote true or false for a parameter? How do we denote it in terms of a type? Can anyone tell me? It's a Boolean. It's true or false. And by default, it will be false, that they're initially infected. And guess what this will now depend on? This condition here. Under what condition will they go down this path to become infective? if they're what? If what is true? Ladies and gentlemen, they'll go down this path if what is true. I've just added this thing here that says, are they initially infected? This is true or false. Okay? Under what condition would they go down this path?
If the parameter is true.
If the parameter is true, you got it. Is initially infected is true. Okay? So we're going to have the population tell the person, you're infected initially, you're not infected. Great. Great. Ladies and gentlemen, okay. Okay, so now let's go. Who's going to tell the person whether or not they're infected? What thing? Remember, a parameter serves to encode an assumption and to communicate it from the point where it's created to the thing that holds the parameter. Where is a person created right now in the model? In what? In the population. So it's in the population that we're going to flip that coin as to whether the person is infected, okay? So I would like to propose adding a parameter to main called fraction initially infected. Are we okay with that? To main, we're going to add fraction initially infected. Okay? Okay, Kurt, I just added a parameter to main called fraction initially infected. And in person, we had this parameter, which is a Boolean, is initially infected. And this branch was only traveled down if this parameter were true, is initially infected. You only go down this branch if they're initially infected. So we have this conditional thing. This is just the default. If nothing is specified, I could call this no initial infection transition if I wanted to, just to make it clear. Kurt would probably dislike it, but that's okay. And this is the initially infected transition. And then over here, I just added a parameter called fraction initially infected. And now for the population, you'll notice that we can specify. Now this is a puzzling thing with any logic. Okay, for the population, we now have this thing is initially infected. Do you see that? So who needs Krugerian help? Do you see this thing? Why do we see this? Why is that in the population? Because now we have this, oh, wait a minute. Okay, yeah, sorry, tone out for a second. Yeah, so this is in the population here. We have this thing, sorry, I was looking at the wrong thing here. Okay, hold on, okay, yes. Population, yeah, tone out here. Okay, initial number of agents is initially infected is the only parameter for those in the population. So what is this asking for? If we did this, what would we get? What would happen if we said yes?
Run it.
Yeah, okay, sure. What will happen if we do this? Okay. So, so let's go down to the level of a person, and what's going to happen? Oh, look, this first person, they're initially infected. Let's see the second person. What do you think they'll be? They're infected too. They're infected as well. They're infected. They're infected. Everyone's infected. Right? Okay. Why are they all infected? Well, we basically said everyone's infected here.
Everybody has the same initial value.
Everyone has the same initial value. We don't want that. What we want is, does anyone recognize this equal sign? Where have we seen that before?
The dynamic.
Yeah, we saw it before in the properties associated with things like the oval, remember that? To distinguish between a static value, that's true for all things at all times, versus this. So we want to actually click this to have a value editor. And what we want to do is we want to flip a coin as to whether a given person, so this is going to go through, when each person is created, it's going to go through and say, is that person initially infected? For each person, it's going to do what we tell here. And what we want to do is, for each person, we want to flip a coin. And the way we flip a coin in any logic, with a certain probability of being true, certain probability of having the loony up, of having the eagle, is it an eagle? Yeah? An eagle up, right? On a quarter?
Oh.
Is that it? Do they have eagle on the quarter? What is it? What's on a quarter? An eagle?
Yeah, an eagle.
An eagle, okay, yeah. Certain probability of having the eagle's head up, right?
Aren't you American?
Well, I've forgotten what's on the quarter. It's been too long. Okay, so we'll do random true fraction initially infected.
Kind of like the uniform 0 to 500 that we did before,
Yeah,
where you specify each person grabs from a uniform distribution, but each person has a separate value for x and y. And you're saying, well, like with the distribution, so each person's sampling. So this is the same thing as you're sampling from this. It's a true-false distribution.
you're basically, for each person in turn, to determine if they're initially infected, you're going to flip a coin. Flip a coin with this probability of being true. We actually saw this yesterday. We used random true. Does anyone remember where? It was when someone got a message of exposure to figure out did they get infected or not. We had random true, this thing. So this is going to return true with this probability, false otherwise. Are we okay with that? Are you okay with that? Okay, here we go. Okay, there we go. Okay, so ladies and gentlemen, now let's go down to the level of a person. And here's a person who's susceptible, person who says, oh, we forgot to say what fraction are initially infected. I'm going to say 50% are initially infected. Okay? 50% are initially infected. By default, it was 0. Okay, ready? Are you ready? Okay, let's let it rip. Okay, here we go. Boom. Let's go down. There we go. Is initially infected false, true, false, false. So some people start initially infected and others not. Okay. But ladies and gentlemen, we're not really seeing the infection spread. How are we going to make these people's color change when the infection spreads? How do we do that? Does anyone remember from yesterday? There's many ways to do this, but let's suppose we want to use the same scheme as yesterday. Green, red, and gray. How are we going to do that?
Create a variable.
Create a variable. Good. Good. I like it. It's not the only way, but it's a tried and true way. And this is spelled color without a U. Okay. Okay. And we want to set it to be of type other, and it will be color, capital C. Do you remember that? This is the same stuff we're doing yesterday. In general, the stuff you learned yesterday is like the core stuff of any logic agent-based modeling. That's like the core repertoire. We're just reinforcing this now. Okay, it doesn't keep on growing. There's a core set that you keep on reusing. And if you work enough at that, you'll get very familiar with it. And the rest, there's some learning to do, but it's going to be pretty mild. We'll make it an initial value of black. Okay? And then, how are we going to make it so that when they become susceptible, they turn green? Riddle me that. Can anyone tell me? How are we going to make it turn green when they're susceptible?
Color equal.
Color equals green, and then what do we need? Semicolon, because we're telling it, do this. Do this. Make this happen. Okay, are you ready? Okay, how about for infective? Color equals what?
Red.
Red. And for recovered, color equals gray. Gray. Not EY. You don't like gray? It's like it's no longer burning. It's ash. Are we okay with that? Okay. Now, it's good practice to color these things manually to reflect the colors that are used visually. Color is an underutilized attribute in my models and in models of many, but it can be used very fruitfully. In fact, one of my graduate students, Alan, who was helping, he's currently writing something on the use of color and visual elements in models. And it's a very useful thing. It's underutilized, but it can be really good for communication. So I just colored these things green, red, and gray. That doesn't actually change. Oh, this is silver, it says. Okay, I guess this is gray. Boom. There we go. Okay, great. Shall we run it? Oh, wait. Is it going to change color? What still remains? Is it going to change color visually? Just because we assigned to color variable, is it going to change the color of the person? What do we have to do?
Go to the person, go down to...
Okay, yes, but now there's the rub. Yeah, so this person is not an easy person to get along with. So there's a trick to it, but I need to show you the trick, okay? That's why we started yesterday with a circle. We started yesterday with a simple geometric object. For the person, there's a way to do it, and it's actually straightforward once you know it, but there's a trick, okay? So get this person, the best way to do it is to probably go over here to the project, and now go to person and expand the presentation. You'll see there's a thing called person, and you'll see inside of it there's a thing called shape body. And you'll notice there in shape body you can set the fill color. But what do we have to do to set it so that it depends on color? Sorry?
Click on that thing.
Click on that thing. Okay.
Just say that every answer.
Yeah. So we have to click to make it a dynamic value. So it's not a static thing. It's not a fixed thing. It's a dynamic thing. Since it goes to this. Are we ready? Okay. Okay. Very good. Okay. There we go. Now we're starting with 50% infective. Can we make it start with just few infectives? Is that okay with you? Instead of 50%, let's make it 5% initial infection. What do you think? 5% initially infected? So where do we set that? Where can we set that?
Fraction.
Yeah, in the experiment, right? In the experiment, because it's a parameter now. We don't have to go back and futz with the model to change this. We can just change it in the experiment to say 5%, right? So I changed it to 5%. Are we okay with that? Okay, so let's run it. Population size 250. Here we go. Okay. We have here a spread of infection over a network. It started with just a few people, but it spread very quickly. Ladies and gentlemen, we are using, just to be clear about this, we're here using a random network. Two people are connected with equal probability. No matter where they are in this circle, they're connected with equal probability. As a result, the infection tends to spread very quickly. Now note that this is the assumption in a random mixing model. If you have random mixing within an aggregate model, you're going to have people bumping into each other from any components of the population, absent a mixing matrix and stratification, and you're going to have very quick spread. Even with a mixing matrix, the assumption is going to be, if you're in one compartment, someone else is in another compartment you're mixing with, you can mix with any of those people in that compartment with equal likelihood. By contrast, here we have the option of putting in place structured networks that are persistent. Sean, do you have a question?
It's not like that. The bathroom would be.
You bet. You bet. I'm going to just finish this up. It'll take less than 5 minutes, and then we should be able to go. Is that okay? Yeah. Okay. So, ladies and gentlemen, the infection spreads very quickly on this mode. By contrast, if we go and impose a network here that is let's suppose a small world network where 95% of the connections are local, we are going to have a situation where it'll start, and it's only when it hops to one of these long distance connections that it will cross easily. Okay, this sort of network is a cross between the random network. It's a step down from random in the sense that you don't have ubiquitous long distance connections, but you can still get connections that ferry the infection from one area of the network to another over long distances. So you can still have relatively fast speeds. It's not entirely localized. By contrast, on the other extreme, ladies and gentlemen, we could go up to Maine and we could choose a ring lattice network. Here, same number of connections, but they're all very localized. What do you expect to see for infection spread here? Well, it'll be very slow because it has to occur along this periphery. There's no way to jump. There's no sparks which float up in the air and land somewhere else and cause a conflagration. Instead, it moves laterally. Okay, there you go. It moves along the ring. So these different types of networks have rather different dynamics associated with them. The infection will tend to spread slower and in a fashion that can be more easily firewalled in very localized connections, be they 2D, distance-based, or 1D ring lattice. And by contrast, in a random network, you have connections from one side to the other of the network very readily. And in a small world network, you have a mixture of that and very localized connections. And that mixture tends to lead to fast spread with a significant fraction of global connections because the global connections allow it to ferry it over the network. Even if it's just at a few small points, it can spread quickly once it's over. So these are a couple types of networks. We've just gone over SIR networks, spread of infection, using messages, once again, to remember the essentials. And we've shown a couple features. Coming back from the bathroom break, we will see how we can very fruitfully use those special parameter values where we can specify the units, and we'll add an open population. So we can have people dying, bursts, migration into this model. Okay? So that'll be after the bathroom break. Thank you for your patience.
Upload where you are because Dominic would like to actually try.
You bet. You bet. I'll do that right now.